So, hey everyone, this is Animesh, and today we're going to talk about a paper titled Slice Consistent 3D Volumetric Brain CT to MRI Translation with a 2D Brownian Bridge Diffusion Model. This paper explores a problem that lies at the intersection of medical imaging and deep learning, specifically how we can generate high quality MRI scans from CT scans using a new kind of diffusion model. And as you'll see, this is not just an academic challenge, but a potentially impactful solution for real world healthcare. Let's first understand the context. Medical imaging is a cornerstone of modern diagnosis, especially for neurological conditions. And two of the most common imaging modalities are CT, or computed tomography, and MRI, or magnetic resonance imaging. CT scans are fast, relatively inexpensive, and widely available. They are often used in emergency rooms because they can quickly detect bleeding or fractures in the skull. However, they suffer from one major drawback: poor soft tissue contrast. That means it's hard to clearly distinguish between different types of brain tissue. On the other hand, MRI scans offer superior soft tissue detail. They are much better for detecting conditions like tumors, white matter lesions, or structural deformities. But they are also more expensive, require longer scan times, and may not be available in urgent or resource limited settings. So, what do you do when you have a CT scan but would prefer the level of anatomical detail you'd get from an MRI? That's where the idea of image to image translation, or eye to eye as we can call it, comes in. And this refers to the process of converting an image from one modality to another. In this case, we want to synthesize an MRI image from a corresponding CT image. In essence, generate a virtual MRI without actually scanning the patient again. And this has a ton of potential benefits, like cost savings. You don't need to use expensive MRI scanners as frequently. Improved accessibility. Rural or emergency clinics that have CT scanners but not MRIs can still get MRI like insights. And better diagnostics. Radiologists and neurologists can interpret CTs with greater confidence when supplemented by synthetic MRI quality detail. So the motivation is clear, but the solution is not that simple, especially when we get into the limitations of existing generating models. So you might wonder, why not just train a deep learning model to do this? As it turns out, several approaches already exist, including GANs and more recently diffusion models. Diffusion models are a type of generative model that have been used to produce incredibly realistic images. In the medical domain, they have been explored for tasks like denoising, super resolution, and modality translation. But there are two big problems when applying these models to medical imaging, particularly 3D volumetric scans like brain MRIs. First, stochasticity. Diffusion models typically start from one random noise and denoise the image step by step. That means even when you provide the same CT input multiple times, the model may generate slightly different MRI outputs each time. For consumer applications like image generation, that might be fine. But in medicine, consistency is critical. Doctors cannot rely on random variations. And second, slice inconsistency. Another problem is that many diffusion models work on 2D slices. When you generate each MRI slice independently from CT, you end up with inconsistencies across the 3D volume. For instance, the brightness may change unpredictably from slice to slice, or anatomical structures might appear disconnected. That's a serious issue when interpreting medical volumes. Some researchers have proposed using 3D diffusion models to handle the full volume at once. While this can improve consistency, it also introduces new problems, mainly high memory requirements, longer training times, and more complex architectures. These models are often impractical to run on standard GPUs, especially in hospital settings. So the challenge is, how can we generate a consistent, high quality 3D MRI from a CT scan using a method that is efficient, reliable, and usable with limited computing power? This paper tackles that exact challenge with a novel approach. It proposes a system based entirely on 2D models but enhanced with two innovative techniques. First is SKC, or style key conditioning, which makes sure that the brightness and contrast are consistent across slices, and the second one being ISTA, or interslice trajectory alignment, which ensures that adjacent slices follow a coherent anatomical path, essentially maintaining the shape and structure of the brain across the volume. And both of these are built on top of something called the Brownian bridge diffusion model, or BBDM for short. You'll hear more about that from the next speaker, but for now, just know that this model allows for deterministic generation, meaning it does not rely on random noise the way traditional diffusion models do. So together, these components make it possible to achieve high quality slice consistent MRI generation using only 2D inputs and without the computational burden of full 3D models. With that, I'll now hand over to the next speaker who will walk you through the technical foundation of this system, the Brownian bridge diffusion model.
Thank you. So I'm Kavya. Now let's take a deeper look into the technical core of proposed approach, which is the Brownian bridge diffusion model, or BBDM for short. To appreciate what BBDM contributes, let's first revisit how a standard diffusion model works. In traditional diffusion models, we generate images through a two-step process which includes a forward diffusion phase where the image is gradually corrupted with noise over several steps, and a reverse denoising process where the model learns to remove that noise step by step to reconstruct a new image. This approach is very powerful, but there is a key limitation. It usually starts from random noise and it's stochastic by nature. The randomness poses a serious problem for medical imaging where reproducibility and accuracy are crucial. We can't have different MRI outputs for the same CT input every time. This is where our approach BBDM comes in. The idea behind BBDM is to model a transformation between two images, in our case a CT scan and an MRI scan, as a Brownian bridge. This is a special kind of stochastic process that starts and ends at fixed points. Instead of starting from noise, it creates a smooth bridge from source image to the target image. In this context, the source image is a CT slice and the target is an MRI slice. The Brownian bridge sets up a probabilistic path that connects these two step by step in both forward and reverse directions. The key advantage here is that BBDM doesn't need to learn noise from target. It learns a conditional mapping from one meaningful image to another. This allows for a fully deterministic generation, which is exactly what we want in clinical applications. Let's look at it more formally. The forward process in BBDM is defined as a Gaussian distribution whose mean interpolates between the source and the target based on the current timestamp. The model learns a score function to estimate the noise at each step and uses this to guide the reverse process. One notable feature of this model is the incorporation of a new term called as the guiding term in its loss function. This term provides direction from CT to MRI, which helps the model not just denoise, but denoise with a clear goal in mind, which is to reach the correct anatomical structure. The actual loss function is based on the evidence lower bound, or elbow for short, which includes this directional term along with the standard denoising component. What this means in practice is that the model becomes much more stable during training and can produce high-quality translations with fewer sampling steps. Here we can have a look at some more details. So the forward process is defined as that distribution which can be easily derived using closed form Gaussian, and the reverse process is also defined like that. The model parameters are trained in such a way so that these both distributions become identical, and the training is done using a simplified evidence lower bound as given in the picture. Another strength of BBDM is its flexibility. Since it doesn't require a random initialization, we can condition it on additional information like style keys, which we will discuss next. This conditioning ability is what makes the model suitable for building deterministic pipelines like the one proposed in this paper. To recap, the Brownian bridge diffusion model connects CT to MRI via a probabilistic path that is learned during training. It avoids randomness in generation phase, making outputs deterministic and reproducible. It also conditions on style and structure, making it a natural fit for techniques like SKC and ISTA. Most importantly, It forms the backbone of the author's proposed methods and makes the entire approach possible using only 2D slices. In the next section, we will see how style key conditioning is integrated into this framework to further improve the consistency across slices. Over to the next speaker.
Hello, I'm Aditya Mishra, and now let's look at style key conditioning, the first of two novel techniques that is proposed by the paper. In medical imaging, especially MRIs, we often see variation in imaging style. Even two MRIs of the same brain can differ in contrast, brightness, or tone depending on the scanner settings, site protocols, or even the patient's positioning. This variation, while sometimes subtle, can cause inconsistencies, like variation of brightness or tone from one slice to another, while generating a 3D volume slice by slice using a 2D model. This inconsistency is what is known as the global style inconsistency, and it's a serious problem in CT to MRI translation. Style key conditioning is designed to solve this exact problem by conditioning the model on a style key. In this context, a style key is a compact, quantitative representation of the overall style of an MRI scan. Specifically, the paper uses the intensity histogram of an MRI image. This histogram describes how the pixel intensity are distributed. For example, how much of the image is bright versus dark. It also includes the cumulative histogram and the derivative, which provide a rich snapshot of the image tone and contrast. The reason why the paper uses histogram is because it's lightweight, interpretable, and most importantly, independent of the anatomical structure. This means that the style key represents how an MRI looks and not what it shows. This is perfect for guiding a generative model while keeping anatomical features grounded in the CT input. Now moving on to how it works. During training, the model receives three input, a group of CT slices as input called yi, the corresponding MRI scans as target called xi0, and the style key cx as kc based on the histogram of the target MRI. The objective is to train the Brownian bridge diffusion model to predict the noise-latent MRI slice xt at time t conditioned on all of this. So this loss encourages the model to denoise XTI by accurately leveraging both CT information and the style key, aligning the generated image with both the anatomical structure and the intended imaging style. The model learns to map from CT slices to MRI slices in the context of that specific style key. This means that instead of trying to average out all possible MRI appearances during training, which can lead to inconsistent outputs, the model knows exactly what style to aim for, guided by the histogram. This does two things. It ensures that all generated slices in a volume share a coherent image styling. It also allows for explicit control of the style during inference. For instance, you could feed in the histogram of a standard reference plane and have all your outputs match that style. An additional bonus is that it makes the model robust to domain shift. SKC allows the model to harmonize outputs by matching them to consistent style key, helping reduce variability across institutions. As you will see later, the paper tested three versions of SKC, the SKC colon, which uses colon 27 average pain histogram, SKC average, which uses the average histogram from the training set, and the SKC best, which uses the actual histogram from the target ground truth. This is only available during evaluation but serves as an upper bound. All these versions significantly outperform models without any style conditioning. Even the average histogram leads to much better style consistency across slices, and the colon 27 reference style produce visually appealing and harmonized volumes. From a technical standpoint, style key conditioning is very efficient. The histograms are small, only 128 pins per channel, and easy to compute, and injecting them into the model involves a simple cross-attention mechanism, so there is no need for additional complex module or huge computational overhead. In conclusion, SKC is a clever and effective way to impose global style key conditioning on 2D diffusion model. It leverages the simplicity and power of histogram representation to bring interpretability and control to generation process. This not only improves visual quality but also opens the door to practical development in clinical settings where consistency and reliability are non-negotiable. Next, we'll look at how the second technique, interslice trajectory alignment, complements the style key conditioning by ensuring local slices consistency in terms of shape and structure. Over to the next speaker.
Hello everyone, I'm Aditya Sharma. Thanks. Now let's move on to the second major innovation in this paper, which complements SKC. It's called Interslice Trajectory Alignment or ISTA. So before we dive into how ISTA works, let's first understand the problem it's trying to solve. So in 2D slice-wise generation, which is common in medical image synthesis, each slice is generated independently. While individual slices may look good in isolation, when we view the entire 3D volume, problems start to appear. Specifically, adjacent slices may not align structurally. This results in discontinuities in the sagittal or coronal views. Where smooth transitions are expected, you might see sudden jumps in anatomy, brightness, or structure, and in clinical context, such inconsistencies can be misleading or even dangerous. So the core issue is local inconsistency between neighboring slices. To address this, the authors introduce ISTA, which is Inter-Slice Trajectory Alignment. It's a mechanism with two main components: co-prediction, which encourages smooth transitions across slides, and correction, which ensures that predictions remain medically valid and realistic. ISTA ensures that even though the model operates purely in 2D, the outputs are 3D consistent. Now, if we talk about how ISTA works, let's now break down the key idea behind ISTA step by step. ISTA works in two phases. First is co-prediction. So in this, instead of generating each slice independently, the model now takes overlapping windows of three slices, say slice I minus 1, I, and I plus 1. This window provides context from neighboring slices. The model predicts the noise for each slice using these windows. Since a single slice may appear in multiple windows, it receives multiple predictions. These predictions are averaged to produce a consensus noise estimate. This ensures that the generation of a slice is informed by its neighbors, promising smooth transitions. Now, if we talk about the second phase, that is correction. Once the co-predicted estimate is obtained, we apply a deterministic correction step. This doesn't involve noise. Instead, it uses a score function that gently adjusts the prediction to fall on the manifold of valid medical images. The score function is based on the gradient of the log probability, and the corrected sample is updated using this function. This helps the output become more realistic and medically plausible while staying aligned with the neighboring slices. Together, these two steps ensure that the final outputs are coherent across slices, Deterministic means no randomness, efficient and parallelizable. And even more impressively, that a 2D model can behave like a 3D aware. Now I'll talk about ISTA algorithm. So now that we understand the concept, let's look at the ISTA as an algorithmic procedure step by step. Start with a noisy set of 2D slices at a certain time step. For each slice I, extract a window of three slices I minus 1, I and I plus 1. Predict the noise for slice I using this window. Repeat this for all overlapping windows where slice I appears. Average all the predictions for slice I to get a consensus noise estimate. Apply the correction step using the score function, that is this function. Repeat this process at each diffusion time step until clean slices are generated. So to wrap up, ISTA tackles the crucial problem of local inconsistency in 2D slice generation with a clever combination of co-prediction and correction. Without needing a full 3D model, it brings structural coherence across slices and enables high-quality, clinically reliable 3D volumes. It's simple, elegant, and efficient, and a key reason why the proposed framework performs so well in both visual quality and downstream tasks. That's all from my side. Thank you.
Thank you. Now, let's shift to the experimental evaluation, which is crucial for understanding how well the proposed method work in practice. The author designed a robust and comprehensive evaluation to compare their method, the 2D Brownian bridge diffusion model with SKC and ISTA against 2D and 3D models. They conducted experiments on two datasets, an in-house paired CT-MRI datasets which provide perfectly aligned ground with truth images, the BRATS-203 FLAIR T1 dataset, a public benchmark commonly used in brain imaging research. Let's first talk about the baseline models they compare against. These include mask GAN, a GAN-based method adapted for pairing training. Second is palette, a 2D conditional diffusion model designed for general image translation. Third is RevGAN, a reversible 3D GAN model. And fourth is ALDM, a 3D latent diffusion model which reduces memory by operating in a compressed latent space. Each of these models represent a different design philosophy from 2D unpaired GANs to high capacity 3D diffusion systems. So this comparison is quite far and broad. In terms of evaluation matrices, they used NMR-SC, normalized root mean square error, which penalizes the pixel-wise differences. Then PSNR, peak signal to noise ratio indicating reconstruction fidelity. SSIM, structural similarity index, which evaluates perceptual similarity, especially in terms of texture and structures. Now, let's look at a result. As you can see in Table 1, on the in-house CT-to-MRI dataset, the proposed method achieved an NRMSC of 0.0515, the lowest among all methods, PSNR of 2.666, the highest in the group, and SSIM of 0.9199, indicating excellent structural fidelity. Even more impressive, this method outperformed 3D models like RevGAN, ALDM, despite being entirely based on 2D slides. This shows the strength of SKC and ISTA in compensating for the lack of full volumetric modeling. The same pattern held on BRATS-2023 FLAIR T1 dataset. The model again showed superior PSNR and SSIM compared to both 2D and 3D baselines, highlighting its ability to generalize across datasets and imaging modalities. But the author didn't stop at comparisons. They performed ablation studies to understand how each component contributed to performance. For SKC, they tested different conditioning strategies. First is no SKC, the baseline BBDM. Then SKC with average histogram from training data. Third is SKC using Collins histogram. Fourth is SKC using the ground truth histogram from the test volume. Now, for ISTA, they tested co-prediction only and full ISTA with correction. The results in table 2 clearly demonstrate how each components add value. Even basic SKC significantly improves style consistency. But for instance, SKC average alone improved SSIM from 0.89122 to 0.9157. Similarly, full ISTA, which includes deterministic corrections, consistently gave the best results, proving the importance of both co-prediction and correction phases. Now, what about qualitative results? The paper includes side-by-side comparison in coronal and sagittal values. Baseline 2D methods showed noticeable inconsistency, sudden brightness changes, distorted anatomy, or even missing features between slices. In contrast, the proposed method produces volumes that were smooth, coherent, and highly reliable in both structures and styles. Radiologists reviewing these images would likely find them far more trustworthy for diagnosis. Finally, a word on efficiency. Despite its superior performance, the proposed models remains lightweight. It uses 100 DDIM sampling steps, half of what models like Palette require. It also avoids the GPU burden of 3D models entirely. This makes it practical for deployment in hospitals with in limited computational infrastructure. To summarize, the method consistently outperformed both 2D and 3D baselines in terms of error, perceptual quality, and structure. SKC and ISTA each made clear, measurable improvements, and it is efficient, robust, and generalizable, showing strong results on multiple datasets. These experiments strongly validate the core thesis of the paper that with small conditioning and sample strategy, a 2D model can achieve and even exceed the performance of more complex 3D systems. Now, I'll hand it over to the final speaker who will discuss the conclusion and future directions of this work.
Hi everyone. I will wrap up our presentation by summarizing the main contribution of the paper, talking about why this work matters, and briefly looking at what could be done in this future. So, this paper brings forward a smart and practical idea using a 2D diffusion model with two simple add-ons called style key conditioning and interslice trajectory alignment to create 3D MRI scans from CT scans. The That might sound simple, but what is really impressive is how the author managed to balance two important goals: keeping the method efficient while also ensuring that the generated images are consistent across slices. So here are the key points. First is deterministic 2D diffusion. So Insight insists of starting from random noise like most diffuser models do, like denoising probabilistic models. This method begins directly from the input CT scan. This makes the process more stable and reliable, something that is very important in medical applications. Second is SKC, which is also known as style key conditioning. So these techniques help all the MRI slices look like they belong together by keeping the same style across the whole images. It even allows you to control or match the style, which is helpful when combining data from different hospital or scanners. Third point is interslice trajectory alignment, or ISTA. So ISTA makes sure that each slice is generated in a way that's line up with the others. So there are no weird jumps or mismatches between them. So basically, it what do it's parallelly makes all images in a parallel way and see the whole images is like 3D. It gives the feeling of a full 3D models without the high cost of accuracy which actually using one. The last point is better and faster result. This matter not only perform better than other 2D models, but it also computes with heavier 3D models and does so well being quicker and use less memory. So from a clinical point of view, this is a big deal. Many hospitals do not have powerful computers, so running complex 3D model is not always realistic. But this approach offer a lighter, faster, and more practical solution that can actually be used in real healthcare settings. Uh, Another point is also it is a flexible method. While this paper focusing on turning CT scan into MRIs, the same idea could work for further tasks too, like converting PE to MRI, improving MRI consistency, or in generating synthetic CT images. Another thing is the SKC method is also very useful in multi-center studies, where different scanner produce images with different style. SKV SKC helps standardize the output, make it easier to train reliable models. So in the second page, we will looking ahead. There are some exciting possibilities. So we will discuss some points like unpaired training, multi models, user control, and real world testing. So in unpaired training right now, the method needs paired CT and MRI data to train and give the result. But in the future, using unpaired data like in cyclic games could make it even more useful. Second point is multiple models. The models could be extended to handle more than one input or output types, helping with more complex clinical tasks. The third point is user control. Since the model already allows some style control, we could eventually give doctor tools to adjust things like image contrast to suit their needs. The fourth point is real world testing. Finally, this method needs to be tested with a real doctor in clinical workflows to see how well it performs in practice and how it could be improved for real use. Finally, in short, the papers show that it is possible to generate accurate, consistent, and even customizable 3D medical images. And using only 2D models and some clever designing, it is great example how we can combine solid research with real world impacts. Thank you for listening. Goodbye.